Hi, this is Phi, architect of the Geometor project, and today is February 14th, 2018, and it's also the day for the first video for the Geometor project. There are so many things that I want to talk about, but today I decided to spend some time talking about the Geometor Explorer, which is a fundamental tool for the Geometor project, where we are investigating instances of the golden ratio, golden sections, within a constructive geometric field, and doing so algebraically. So what you're seeing on the screen right now is the first instance of the Geometor Explorer with a very simple model. We have 4 circles and 2 lines, and I'll explain a little bit more about some of the dynamics of what's happening here. I think the best way to do that is to have it redraw the model again. So I'll just click draw up here. And you can see we begin with 2 points, and we draw a line between them, and then we draw circles using those 2 points with the centers on either side. And those would be unit circles. We then draw 2 more circles with a radius of 2 from those original 2 starting points, and then draw a bisector line down the center. And you'll notice that there were golden bars that were flashing on the screen towards the end. These are golden sections that are found by the Explorer as it examines each of the lines. Once it's finished a geometric construction, it will go through and actually look at each of the segments on all of the lines and see if the segment that is next to it holds a golden ratio proportion. So it's actually discovering this on its own. I'm not telling it. And here on the side, you'll see a list of the points, a list of the lines, and a list of the circles. Here for points, we're seeing expressions like 1/2, 3/2. Here we have the square 1/2 times the square root of 3, and these are all algebraic expressions that are being shown here. So all of these values are being carried through algebraically. We're seeing lines that are being formed here. The first 2 numbers are the indexes of the points that are being used for the lines, and then the equations that are being formed from those. Same things for the circle. Here I've got the center point and its radius and the equation that results from that. And then down here are the segment pairs that have been found within the drawing that are within the golden ratio. All right. So as Explorer is going through and finding these instances of the golden ratio, it's making this list, and then it allows me to actually animate the creation of these segments using only the ancestors that are from this model. Right. So if I begin to show this now, it's going to mute all the elements. And then show you that that pair of golden segments, only those, that other circle is really not required for that. And we'll do that again here. So this is a pretty simple model, but you'll see as we get into more complex constructions that being able to see just the elements that are necessary to create the segment is an important part of the pattern, an important part of, how did this thing get here? So I haven't said anything yet about this particular model. As you begin to look into the creation of golden ratio constructions or golden sections, you start to ask the question, well, how many different ways are there to create it? And what are some of the simplest ways to create it? So if you remember from constructive geometry, we have only a straight edge and a compass to work with, and that means both of those tools require 2 points in order to operate. So in our field, we begin with 2 points as a given. Those are the only givens within our field. Everything else is constructed from points that are derived from the field. Right? And as each element is being added to the model, the intersection points are being determined algebraically through the equations. And then when I hover over items, say like this point over here, I can actually see its value as an algebraic value down here. And that goes true for each of the circles as well, and each of the lines. You can see their expression. This one here actually needs to be reduced. It should just be x equals 0 here. But it's really quite interesting. So it's finding all of these points algebraically and setting them up, and then finding that instance of the golden ratio. We'll look at the code later, and I'll show you a little bit about how it's doing that. This is, the fundamental aspect of what the Geometor Explorer is doing, and the idea is to be able to capture all of these instances of the golden ratio and begin to look at them holistically, as a set, basically, and then we can start to ask questions about them. So this particular instance of the golden ratio, which is really quite a beautiful construction, right? I mean, here we just have 4 circles that that are each concentric, and the first 2 circles share a radius. There's something just really beautiful and confined about this, and that center line down the middle actually creates instances of the golden ratio right there at the very beginning. And this is, I think, what is probably going to surprise many of you if you're interested in the golden ratios, to see the preponderance of instances and just how they appear within so many different sets of proportional systems. And I'll try to isolate some of those so that we begin to look at some of the traits and how it actually appears and comes into existence. And then where we have overlapping points that happen with different proportional systems. All right, so let's jump over to GitHub for a second, because I do want to talk about that as an important part of what we're looking at. So the demo that I just gave you is currently in the master branch, and this is under release. This release for today. It's my video log of 2018, February 14th. And so we can see that. And there are 2 other branches that are also at work here, which I'm going to do a separate video on because they begin to talk about some of the other issues that are involved in doing this work. I have an Intersect branch and a Matrix branch, and this is a public project, so please head on over there and take a look. I've got a pretty good write-up here about the Geometor Explorer and some of the basic, fundamental concepts about it, a little bit about classical constructive geometry and the ideas behind that, and a little bit about Cartesian grid and algebra that's set up within it, and then showing you how to set up a script in a main.js in a web page using these tools. Got a little bit about some of the other libraries that are essential in this. Of course, Algebrite is key to this as being the algebra parser for the system. And svg.js is providing the mechanisms for drawing. So I'm using their libraries and also the pan and zoom extension, which allows me, if you didn't notice, to actually zoom in and out of this model. Be able to look at things a little bit more closely. I'm hoping to scale the elements as I zoom, here too. So points would always be the same size on the screen, and that would help to differentiate them as we get into having many more points on the screen that may be close together. Okay, so this is, as I mentioned, GitHub, and please head to the IM5 account and look for Geometor Explorer, and you can keep up with some of the changes there. Definitely, this is a collaborative project. I am interested in all ideas. If you want to take a look at the code and send me a pull request, it's still pretty early right now. I'm still kind of trying to settle in on some fundamental architectural things, but I would love to hear what you have to say about the project. So let's come back now and let's take a look at some of the code, right? So this is a very early prototype here, this version that's in master, and right now this is the index.html page that is coming up. Really quite simple. I've got a body and a main where there's an SVG element that holds the drawing. The aside is the sidebar that has these other panels. The panels are just pre-elements, so I'm just taking, I'm just basically dumping logging text into those containers for now. And in the future version, you'll see of beginning to represent that as tabular data, and it's going to start to show a lot more interesting things to us. And then, I was using an SVG prefix early on for my files here, but you can see, I've got utils and algebra and elements. element's probably the most interesting one if we bring that up. There's just a kind of a big bag of stuff that I had going on here. But if I collapse it down, just collapse it down, fold all the code, and you can see that I've got a function that's acting as a point object and a line object and a circle object and a number of different functions that are actually part of those objects for doing various things. One of the things that didn't really kind of become clear early on as I was working on the prototype is that I'm actually building a model, and that this is a model almost like a database, essentially of points and things that connect points, lines and circles. So it's not so much the connections of them, but in them, right? So the points that are a part of a line or a part of a circle are what we're looking for. And I'm maintaining those relationships within a set of arrays here, hoping to become true sets with unique sets of objects within the different sets there. And I'm doing a little bit of management around that here at this point. So early on as a prototype, I was just kind of doing everything in this class, and really by the time I got to this point in the code, I was so ready for a refactor of this to separate some of these concerns. So I've got data representing the point, the x and y coordinates of the point. I have the rendering of the element here. This group points is a group that I created within the SVG object, and I'm adding a circle to it here, and a circle object to represent a point. I'm adding this point to its parent point collection. I don't know why the point would do that itself. Shouldn't do that itself. Wiring up a bunch of hover events and UI events, and then a couple of helper functions and all that kind of stuff. Right. This has been changed radically, so I won't go too deep into this. But the line was kind of working the same way. But an important part of all of this, when we get into the elements of the lines and circles, was how to determine where intersections were happening. And so if I close this back up, let's see. We'll go here. After I create each element, as you can see, I then iterate through the elements collection and check to see how this line intersects with all of the other elements in the collection. Right? And so basically every time an element is getting created, there should be a process that goes through to check to see if that element intersects with any of the other elements in the model. All right. This can actually get a little bit time consuming as the model gets bigger. And there's a couple of other places where we've got some iteration through things that can get a little time consuming, especially doing intense algebraic work. And so any insight on how to improve some of the logic around this would be appreciated. Right. So we come down to line intersect here. There's a bunch of conditional stuff that was happening around, trying to determine how to figure out an intersection. And right here at this point, I was still thinking about intersections with respect to the nature of the objects that were in them, right? So I knew how to intersect a line and a line. I knew how to intersect a line and a circle, and a circle and a circle. So it's separate operations for each of those. And again, right around the point of getting to here, and then starting to experience some problems, I realized that it'd be much better to try to approach this in a more generalized way, right? So could we begin to create equations that were generalized, that using the same form, whether it's a line or a circle? And I think I've solved that, and we'll talk about that in the next video here. So I won't go too far into some of these, but intersect line, just kind of doing some operations. Actually, heavily relying on Algebrite here. So Algebrite really kind of handing scripts over to it, and it's giving me results back. So by creating the variables for each of the equations, then I could actually just subtract these equations from each other in Algebrite. Just do that quite easily, and then grab these values out and do some checking for degrees, that kind of thing. Let's blow this out, open that up. all the rest through away. So there's just lots of conditional logic that was going on, and you can see, trying different things, trying to streamline the process, here, and so lots of different things were coming out of this. I was trying different things, trying to figure out how to maybe more generically work with the intersection of a circle and such. So I won't spend any time on this because I'd rather talk about the new approach here. But you can see this was getting really complicated, and then as the models got more complicated and I started receiving some errors, I couldn't tell where the problem was. I was not holding on to various aspects of the equations more parametrically, and I was passing a lot of stuff over to Algebrite, and it was just kind of a black box, and I couldn't tell if I was passing the right or wrong thing, and if it was giving me stuff back because of my inaccuracy. So that got me down the road of actually looking at creating some diagnostics. Maybe it was here in the algebra function, or I don't remember where I was doing that here. Utils. Anyway, I forget where my diagnostics were. Check all points, check all lines. And I was trying to figure out, how can I create a test harness around this to actually determine if everything is being done correctly. Is there a way of performing these functions differently or using a different set of tools or a different library? I had no way to really determine if I was doing the right thing. Other than right now, if the points that are derived from the algebra don't show up in the right place on the drawing, that's a pretty good indication that I've got a problem. and that's kind of what was happening in one of the earlier versions. So maybe a quick peek here in my node modules. So all of the extensions that I'm using are JavaScript libraries, and they are all being managed by Node for me with the Node package manager. So I have Algebrite and the GreenSock animation platform. jQuery, I don't even think I'm really using jQuery all that much, and whether I really need it or not is a question that's still out there. Cotex for rendering mathematical equations, and then svg.js for drawing SVG elements into the diagram, and SVG pin zoom over here. File saver I brought in. I'm not using it yet, but it's my intention to be able to export these SVG diagrams to actually be standalone diagrams. So they would contain all of the CSS and all of the JavaScript for doing some simple hovers and give you some interactivity with it, but it was still maybe even animating the construction. I could see that easily being embedded into SVG. SVG is a powerful platform, and I'll talk a little bit about what's happening there. And one of the other important aspects of this is using SCSS or SAS for doing the styling, and it's still pretty rudimentary here right now. But the notion was getting certain color palettes together to represent the different objects here, and then using that more consistently through. There's a bit more work that needs to be done here, and I'm having some problems with my SAS processor right now. It's hanging on me. I don't know exactly why, but we'll figure that out in the future. So let's go back to the model. One of the things I want to point out here is that I'm doing quite a bit of logging, and still am in the course of it, and it's getting better and better each time. But the log is actually an important place for showing the work of what's happening here. So you can see every point, every line is being created. As the line is being created, it's telling me which points are doing it, and then showing me coefficients for each of the elements. Same with circles and all of that. So I've got some traceability, but I wasn't showing much of the detail about where these points were coming from. And again, that was a black box, and when I started having problems and digging through and trying to figure this out, it wasn't working too well. And once the model is created, we'll come down here. You can see there's a break. It tells me the number of elements and points that were created, and then it starts walking down each of the lines. Okay, here we are, and we're going to take a look now at this root 3 construction. And this is very much the same construction as you saw in the last diagram, with a few additional items that are added, a few lines. These lines here that are following the edges of the equilateral triangles that are being formed, and then this one diagonal line here that is being formed through this point and that intersection point right there, where this line and this original unit circle are intersecting one another, and that intersects our perpendicular bisector right here at this point, and that allows us to create a circle here, which then you can see cuts all of these other lines into golden ratio segments. It's really quite amazing. All of these intersection points here around this circle are creating golden ratio instances. And so this is a fundamental property of an equilateral triangle construction. It's really quite amazing. And I want to show you an animation of this. So what Explorer can do is show each of the golden section pairs and just the parent elements that are necessary to create them. I think that there's a bit of a change that I need to make here. The center points of the circles are not included in the parentage right now, and I think that needs to be. So there might be a few more things that are showing up on this ancestry diagram, but the patterns of these golden ratio instances are quite amazing. And of course, we're seeing harmonics. What I hope to do is not just show pairs, but actually for every segment along the line to show the harmonics that are stretching out from it in both directions, both the greater and lesser harmonic that would be demonstrated there. And I think that would be really quite interesting to see, and it would reduce the number of iterations through this, but still allow a great deal of flexibility in the exploration. So you kind of get the point here. One of the things that that comes to mind is, well, how many of these diagrams that we're looking at are unique? And that's a really important question here. What I'm hoping to be able to do is create a database of really everything that's going on in this model, right? A database of all of the points and all of the lines and circles, which essentially is a graph of nodes and vertices. We should be able to examine that with the same kinds of tools that we would examine any graph. And then we also want to be able to determine uniqueness and then other attributes of these instances of the golden ratio. They all sit there in relation, in some ratio to the unit of this diagram, the unit being the length between the original two starting points, here and here. And so when we look at a particular instance, is it something that is being derived from a unique set of elements, or is it just a mirroring, or in the other side of something that's happening, really with the same elements? And we do kind of see that here a lot, through the construction. And so I want to try to figure out what are those attributes. Certainly, the proportions of lines that are being held together, the orientation of the circle's center and radius to other lines that are being found in intersection with it. All of these things are a part of a pattern that can be examined and cataloged and categorized. For instance, the first golden ratio instance down the center between of this bisector here, which we looked at earlier, is in the ratio of the square root of 3 to the unit. And so would this one here be. Again, another interesting, kind of relationship. But, are there only certain kinds of proportions that the golden section can exist in? There's a lot of questions that you start to ask yourself. How many different ways are there to arrive at the same point with the golden ratio using golden ratio constructions? How many ways are there to bisect this original point or create an extension out here, as these points are. I'm kind of fascinated by all of the incredible variety of options that there are in doing this, which means that the golden ratio is kind of woven into all of these different kinds of proportional systems. Right. So this I would call a root 3 system, really just because root 3 is kind of the predominant proportion of the equilateral triangle, and all of these lines and circles are, carrying that around with it. And so like this circle here, you can see it's got square root of 3. These lines have the square root of 3, as part of them. So this is all kind of a square root of 3 proportional system, that we're looking at. So let's take a look at square root of 5.